So, extreme range RFID. Couple of points on privacy and safety first. There is only one type of RFID tag that I'm reading during this demonstration. That's the tags that I handed out. It is a commercially available tag. There's lots of others in circulation. So if at any point you're concerned about my equipment reading other tags that you don't want to be read, sit on them. Take it out of your pocket and stick it under your butt. Your backside will actually shield it quite effectively. So yeah, don't worry about that. Or it's not a problem. I'm not going to be able to read through. I'm not using much power here. Secondly, during the demos, there is going to be RF power coming out of this. Not a tremendous amount. It's about a watt, in fact, according to this meter. So it's less power than a cell phone, but please don't touch the antennas if you do walk up. Okay. So what is the RFID technology that I'm using here? It's called EPC Generation 2. Electronic Product Code is the acronym. You compare that to a universal product code. That's a barcode. It's the tags are effectively electronic barcodes, or RFID barcodes rather. They're passively powered. They're UHF RFID. They work at 900 megahertz. If you look at the pieces of paper that were handed out when you came in, you should see a metal strip in it. That's the antenna for the tag. And if you look somewhere in the middle of that strip, there should be a little tiny dot, a little raised bump in the middle. That's the RFID chip itself. So it has a 96-bit ID number. You can get them in different sizes from 64-bit up to 128-bit. There is no security on these tags whatsoever, at least not anything that really means anything. They do support two special codes called a lock code and a kill code. If you set the lock code, you can then not change the tag number until you unlock it with the code again. Likewise, if you set the kill code, the next time you send that kill code, the tag will actually self-destruct. It'll turn itself off and disable itself. Unfortunately, both of these codes are sent in plain text by the reader to the tag. So with a Gen 2 sniffer, you can just pull the codes off the air and there's no encryption. Similarly, there's no access control. There are a couple of proprietary versions of Gen 2 that are extending the basic standard. They support some kind of access control, but again, it's all done in plain text. There is no encryption here whatsoever. Where are these tags used? Well, if you've got a passport card, not the book, but the little card that's good for travel in North America, you've got one of those in there. If you've got an electronic driver's license or an enhanced driver's license that's currently an issue by New York and various other states, you've got a Gen 2 tag in there. If you've ever bought a product at Walmart and got an RFID tag on a label or something like that, again, that's EPC Gen 2. It's very widely used, it's very widely deployed, largely because of its long-range nature. So what is it about EPC Gen 2 that makes it long-range? Well, if you look at a traditional RFID system, it's an inductive coupling. You have a coil of wire in the reader, you have a coil of wire in the tag, you bring the two close together and a magnetic field couples the two together. The reader can then send data to the tag by modulating the strength of that field. The tag can return data to the reader by consuming more or less power from that field. So all the data exchange happens by modulating that magnetic field, as I said. The thing about magnetic fields is that the field strength drops off as the inverse cube of the distance. So unlike radio, where the available energy is the inverse square of the distance, when you're talking about a magnetic system, you're talking about an inverse cube law. So power drops off very, very sharply. You get a few inches away from the reader, and you've typically got not enough power for the tag. There's some pretty fundamental limits involved there. The maximum theoretical read range for a 13.56 megahertz tag is, I believe, about 35 feet. Hard limit of 35 feet. You cannot possibly read further than that, no matter how much power you dump into it. Gen 2, on the other hand, these things are effectively radar IFF transponders. So what happens is the radio waves that are coming in Some of those get absorbed by the tag and are used to power the tag. Others of them get reflected back from the tag. And the tag can actually control how much of that incident power gets reflected. So you can think of it like a radar system. If you imagine this setup here is a radar tower, and you guys holding the tags, imagine the tag is an aeroplane. You can imagine that as the plane tips its wings back and forth and exposes more or less surface area to the incident radiation, the return signal will get stronger or weaker. That's effectively what these tags are doing electronically. So it's modulating its coefficient of reflectivity. That's the catchphrase. Gen 2 is actually a proper backscatter system. A lot of people say that RFID systems are all backscattering, but they're not. Most of them are inductive coupling. This is the only one that I know of that is actually a backscatter system, in that I send the power and the tags scatter some of that power back towards me. Because it's a radar system, it's a radio system, and because it's radio, that means we've got an inverse square law with distance. We're using an electromagnetic wave here. We've got a proper radio transmission rather than a magnetic field and an inductive coupling. So we can use proper radar techniques and proper radio techniques to increase our read range. It's otherwise a fairly typical radio system. There's a few differences from most average radio systems, but it's close enough to a first approximation. So given that we've got a radar system, we can essentially come back to the radar range equation to predict our read range. Now, the radar range equation has lots and lots and lots of different forms. There's lots of ways of substituting out different parameters and, generating a range equation that contains just the parameters you need. This particular form that's on the screen now, this is the form of the radar range equation that I like. This actually came from a company called ThingMagic, who manufacture Gen 2 RFID readers. And this is the equation that they use to model Gen 2 read range. So I'm not going to explain this in detail. I mean, if you know any radio, this probably makes sense already. All I'm going to say about it for the purposes of this talk is that we can see that the maximum range is derived from three things. Firstly, we've got GR and GT. That's the gain of the receive antenna and the gain of the transmit antenna. So the maximum range is derived from the square root of the antenna gain. So if we put 100 times better antenna on it, we'd expect to see 10 times the read range. Likewise, transmit power, PR and PT, that's the transmit power and the incident power that's returned back from the tag. If we up our transmit power by a factor of 100, again, we'd expect to see the square root of that in a range increase. So we'd expect to see a factor of 10 increase. Beyond that, there's a bunch of stuff that we can't control. Lambda is our wavelength. We're obviously, set to a specific frequency here, so our wavelength is dictated by that. There's a few other things that we can't control, but the important point that we can make from the radar range equation is that our read range is fundamentally proportional to the square root of antenna gain and the square root of transmitter power. So given this, we can take an off-the-shelf system and we can scale it up. We're talking about making differences to a system. So we can treat an off-the-shelf system as a reference system, and then we can work in ratios compared to that reference system. Now, the easiest way to do that is with decibels. Raise your hand if you're familiar with how decibels work. Okay, most of you. So it's a logarithmic scale. It's 10 times the base 10 logarithm of the ratio between two numbers. The reason why logarithms are so useful when you're talking about radio is because you can quantify a receive chain or a transmit chain. Each component in that has a certain number of decibels gain or loss. If you were to look at that as an absolute gain value, let's say that my power amp has a gain of 1,000. My attenuator might have a gain of 0.3, and my USRP might have an internal gain of 27.5. If we're working in linear numbers, we have to multiply those figures together in order to figure out what our overall power is. If we're working in decibels, however, we can say, just add them together. If you add decibels together, that's equivalent to multiplying the underlying numbers together. So it's convenient for working the mathematics involved here. Decibels are just ratios. It's a ratio between one number and another. So it's useful on its own for expressing amplifier gain, but not tremendously useful for many other things. So what we can do is we can define one of those points. If we say we've got decibels compared to a reference level, then we get things like dBm. So if we take a reference level of 1 milliwatt of RF power, and we express our transmit power in terms of decibels reference to 1 milliwatt, then we get a unit called dBm. Very convenient. Likewise, you can see I've got two very large Yagis here, or reasonably large Yagis. What these do is they concentrate the radio energy into a narrow beam. It's about 15 degrees wide. So instead of radiating equally in all directions, an isotropic antenna radiates equally in all directions. We have directional gain because we're focusing that energy into one specific angle. So we have gain reference to an isotropic antenna, which is where dBi comes from. So what we can do is we can actually add all of these three different units together. They're not actually really different units, because if let's say I've got 10 dBm coming out of my USRP, I then put it into an amplifier with 100 dB gain, and then I put it into an antenna with 20 dBi gain. I can just add those numbers together to figure out what my transmit power is. It's 10 plus 100 plus 10, or whatever numbers I just said. And you just add those together, and you've got, at the end of it, you've got a measurement called the EIRP, the effective isotropic radiated power. Not a particularly meaningful measurement, but it is a valid measurement nonetheless, and it is perfectly valid to add dBm, dBi, and dB gain to just make life simpler. So I mentioned that these tags work in the 900 megahertz band. More precisely, that's the 902 to 928 megahertz ISM band. The tags actually support a wider frequency range than that. They'll actually go down to about 850 megahertz, because not all countries around the world use the same frequencies for Gen 2. So they're pretty wide band. They're very low power, obviously, and because of the ISM rules, the industrial, scientific, medical rules that govern how you have to operate in this band, they're very low power. The reader is very low power. It's limited to a maximum of 1 watt. It's very low utilization, so it has a low duty cycle. The transmitter is only transmitting for a very short proportion of any given second. It also hops frequency very regularly. Again, this is an ISM regulation. The ISM uses of the 902 to 928 megahertz band, they're actually secondary though. It's primarily a ham radio band, but ham radio operators tend not to like it because of all of the ISM applications. There's so many ISM transmitters in the band that it raises the noise threshold, and from most hams, that makes it just completely unworkable because there's just too much noise. So if we approach the band as an ISM band, then we've got very strict rules on power, on antenna gain, on frequency hopping, all of this kind of stuff. If we approach it as a ham radio band, we've got much less restrictions. So what do we actually get from approaching this as a ham radio band? Well, first off, we need a license. They're pretty easy to get. Ham radio licenses, the questions are all published. It's effectively, open source examinations. The URL that's on the screen now is a parrot-style learning application. They present questions in order, and if you get the question right, they never show it to you again. If you get the question wrong, they'll show it to you again, and they'll keep showing it to you until you get it right. You can